9.2 Example 4. Before we get into Example 4, I first want to get into how do you write a Taylor series when x is equal to a instead of 0. So in our previous examples, x has been equal to 0 every time. Now we're going to show you how to write it when x is equal to a, any x value. So let f be a function with derivatives of all orders, just like before, throughout some open intervals containing a. So now we're not just 0, it's any open interval where a is the x value we're looking at, so 5, 15, or whatever. Then the Taylor series is generated by x equals a is, and it's all of this, which if you notice is exactly the same as the Maclaurin series, except the only difference is right here. Instead of just having x, we have x minus a. And in our series, it's x minus a. And instead of f of 0, it's f prime of a. That's really the only difference. So the partial sum, instead of going to infinity, would be from k equals 0 to a specific n value. All right, now let's talk about example 4. We're going to find the Taylor series that's generated by the function e to the x at x equals 2. So we are going to find the Taylor series that represents e to the x at x equals 2. So step 1 is to write out the polynomial term by term, in order to find that pattern. So remember, if you want to find a Taylor series, you have to find f of 2, f prime of 2, f double prime of 2, f triple prime of 2, and so on until you can start to see a pattern what's going to happen with those numbers. So again, step 1 is to write out the polynomial term by term to find a pattern. So step 1, f of 2. It's going to be e squared, which is, well, there you go, e squared. F prime of 2. F prime is going to be e to the x, so it's just e squared again. Cool. Second derivative, e squared. And already you can see the pattern that the nth derivative at 2 is just e squared because e to the x is its own derivative. So this means that e to the x at x equals 2 can be written as e squared plus e squared x minus 2 plus e squared x minus 2 squared over 2 factorial plus e squared x minus 2 cubed over 3 factorial plus dot dot dot. You can already kind of see the pattern. It's going to be e squared x minus 2 to the n divided by n factorial. Notice that each time I have that e squared, and then I just have x minus 2, and I increase the power by 1. So now the hard part for these, and this one's not too tough, but the harder part for these problems is writing it as a sigma notation. So sigma, n equals 0 to infinity. Now, what's helpful is to identify it piece by piece. So notice that each one has an e squared, so I'm going to need an e squared. Then I'm going to divide that by n factorial, and the reason I'm doing that is this one is 1 factorial and 0 factorial. So each term, this is n equals 0, n equals 1, n equals 2, n equals 3, and then just n equals n. So each time you add an n, it goes up by 1. So that's why you have the n factorial. And then in each term, I'm going to have that x minus 2, and it goes up by 1 each time. So I'm going to go ahead and call that n. And that's it. That's all you have to do in order to find the Taylor series for this one. Okay, on your own, I want you to determine the Taylor series for 1 over x plus 1 at x equals 2. Now, I recommend kind of keeping your work organized and just make sure you find a pattern. So go ahead and try this on your own. All right, so let's give it a try. So I'm going to go ahead and make a table for this. So this will be my n. This will be the derivative in terms of x. And this will be the derivative when I plug in 2. Okay, so I'm going to go ahead and plug in 0 for n, because you always start at 0. So it's 1 over x plus 1. So when I plug in 2, I get 1 over 2 plus 1, which is 1 over 3. Now I'm going to take the step to be writing it like this. It's going to make my derivatives a little easier. So when n equals 1, that's my first derivative, negative 1, x plus 1 to the negative 2, which is negative 1 over x plus 1 squared. So now I'm going to plug in 2, and I get negative 1 over 3 squared, which is negative 1 over 9. Do the next derivative. So I bring down the negative 2, so I get 2 x plus 1 to the negative 3, which is 2 over x plus 1 cubed. So that's going to be 2 over 3 cubed, which is 2 over 27. Do the next derivative, negative 6, x plus 1 to the negative 4. So negative 6, x plus 1 to the 4th. So I get negative 6 over 3 to the 4th, which is negative 6 over 81. So I think three derivatives, 4 terms, that should be enough to pick up a pattern here. So I get 1 over x plus 1 is equal to 1/3 minus 1/9 x minus 2 divided by 1 factorial plus 2 over 27 times x minus 2 squared over 2 factorial minus 6 over 81 times x minus 2 cubed over 3 factorial plus ... Now what I need to do here is I need to go ahead and find a pattern, which is kind of tough, so I'm going to start simplifying and maybe I can find one. So this is going to be 1/3 minus 1/9 x minus 2. Now notice that 2 factorial is 2, so that's going to cancel with the numerator. So I get plus 1 over 27 x minus 2 squared. And then 3 factorial is 6, so notice those are going to cancel. So I get minus 1 over 81 x minus 3 cubed. Okay, so I'm starting to see a pattern come up. So I'm going to rewrite this. Maybe if I write them all with 3's in the denominator. So 1/3 minus x minus 2 over 3 squared plus x minus 2 squared over 3 cubed minus x minus 3 cubed over 3 to the 4th. Okay, so they always have a 3. So that's good. It might also help to write out the terms. So this is n equals 0, n equals 1, n equals 2, n equals 3. All right. So let's go ahead and try to pick apart our pieces. So I know it's going to alternate because it goes positive, negative, positive, negative. So I know I'm going to need a negative 1 to the n. And then it looks like I have x minus 2. And then this increases by 1 every time in the numerator. So it's just n. Because when n is 1, this is 1. When n is 2, that's 2. When n is 3, that is 3. Okay? So then I'm going to divide. I definitely need a 3. But the question is, what is the power? When n is 0, it's 1. When n is 1, it's 2. When n is 2, it's 3. When n is 3, it's 4. So it needs to be 1 larger. So I'm going to write that as n plus 1. So that's my general term, and the only thing you have to do now in order to write it as a sigma is to throw that sigma in front. And that's it. We're all done. We've written it as a Taylor series polynomial.